Hi, I'm Frank Strickland.
I'm Chris Whitlock.
Welcome to this lesson to help you with AI literacy, specifically in the area of ChatGPT and large language models, or LLMs. Chris and I, as a brief introduction, have been working in the advanced analytics and AI space for 30 years in both government and industry. And most recently, we have formed AI leaders to create content that helps promote AI literacy throughout the national security enterprise, and then AI fluency among leaders depending on their role. In this lesson, as you see on the left-hand side, we are going to help you become literate in ChatGPT and LLMs by covering the content that you see here. We're going to give you an introduction that will move to a historical overview of how these models have evolved and are still evolving. Then we're going to lift the hood and let you understand sufficiently understand how these models are actually working. And then we're going to finish up with a discussion of some of the strengths and cautions and limits and what we can be reasonably certain about and what is more uncertain about the evolution of these models.
We've also gotten some important perspective as we developed this, had some people review and provide comments back from various perspectives, former director of the JAIC, a deputy commandant of the Marine Corps, et cetera, to include a couple of really great technical experts in industry. We will share those perspectives as we move through the content.
So if we step back and say, what is the overarching goal? It is illustrated here by this spectrum. As you've probably experienced with AI in general, and certainly in this space around ChatGPT and large language models, there can be a set of people that are really hand-wringing their concern, their legitimate concerns, but that can go to the excess in just kind of being paranoid about these things and not wanting to engage or shut them down or stop them. But the other end of the spectrum, there can be just wild-eyed enthusiasm to the point that it is just sort of conceptual hype. What we're trying to do in promoting literacy around this is to help you strike that balance so that you can understand how to think about where to apply these, how to apply these, how to integrate them into your enterprise for mission impact. So let's dive in and start by, in effect, kind of putting your hands on the keyboard and letting you see a ChatGPT response. So we have put a prompt in that you can see here. How important is AI to the U.S. Air Force? And you can see very quickly that this model has generated a 4-paragraph answer, and it is a very high-quality answer. The beginning paragraph and the end are very topical, the type of quality of writing that you would expect to see in terms of topical sentences, topical paragraphs. The flow between one paragraph to another is very good. And then interestingly, you see in the first paragraph and the last, AI is put within the context of the Air Force's mission. And then the second and third paragraph addresses that in two of what we think are the real broad perspectives that you would talk about AI. One is more in the sense-making and decision-making in the second paragraph. The third is in autonomous systems. So it gives you a sense of how fast you can put a simple prompt in and get a very high-quality answer. Now, let's take another prompt here and begin to introduce you to the performance of these models. This prompt being the Air Force is, a basic STEM, and the model has expanded on that. And we want to have you mindful of 3 features in terms of how the model is performing. And the first feature is just a probabilistic distribution. You see the 5 responses here, and you can see the probabilities of each of the responses as we tick down through the 5. Now, a probabilistic distribution across these 5, This particular one you can see is pretty extreme. One of the 5 has an 80% probability. Many, in fact, I suspect most don't have that degree of weight. The probabilities can be spread out. But in this particular case, what we want you to see is a probabilistic distribution of answers, and then 2 other features. The first being randomness. The model is not going to respond with the most probable answer every time, or the most probable output every time. It is going to randomize across that distribution. We're going to show you this in much greater detail as we lift the hood and look at how it works. But one final feature that we would just highlight for now is temperature. The model can have the temperature, quote unquote, set such that if you dial the temperature way up, you're constraining the model to the highest probability outcomes or responses. If you turn the temperature way down, you kind of expand the aperture and the model's responses draw on the full range of probabilities, and some of those answers then can become pretty spicy. So those are 3 features just introducing you to how the model works that we want you to be acquainted with. Now, let's talk about types of use cases for large language models, and we summarize them with 5 here. The base case, completion, you're very familiar with because it's in wide operation. You probably have it in your email. You're writing a sentence and the email is prompting you, suggesting you a completion to the sentence that you've started, or a word to add as the next word or phrase. Those are base language models that have been developed years ago and put into operation in a number of applications now, email and many others. These other 4 get to a more advanced type of modeling that are referred to as instruction-tuned models. And you see 4 types of use cases here. Summarization, we're going to show you an example, but you take a larger body of text, feed it to the model, and you ask the text to summarize. So think about the massive volumes of text that we have. You don't have time to read everything you want to read. I know I certainly don't, but I'd like to get the gist of many more things than I have time to read. And so the models do a great job, and we're going to show you, of summarizing articles and summarizing them lightning fast. Expand or expansion is just the inverse of that. You've gotten promoted. You're on my team. I want to send you an email congratulating you on the promotion. I can give the model a stem, a prompt, an input that is just a fragment of that email, and it writes the email for me. So it expands the fragment out into a full textual response. Then translate. You can understand obvious one area here is translating between languages. I can take a volume of English text, translate it into French or Farsi or some other language. But there are other types of translation which are really interesting. I can take a body of HTML, hypertext markup language. It's what we use to create websites, for example. And I can have a large language model take HTML as an input and output a different type of text, JSON. And so those are examples, just a couple of examples of translation. And then lastly, infer or answer are analytical use cases where I can have the large language model go into a body of text and basically do what you do in analysis, kind of decompose and differentiate between people. Give me the names out of this text, give me the entities, give me the locations out of this text. So wide range of use cases for these large language models, which is one of the reasons that there's such exciting potential for them. Now, we will want you to be aware of and conscious of, while ChatGPT has kind of sucked all the oxygen out of the room.
It has.
Yeah. It is one model of many, and we are only showing a few here. These models are being developed around the world in multiple countries. In fact, the two models that you see on the bottom row are being developed in China. And so we would just encourage you, as we would do in talking with our community about any type of tool. There are multiple models in development. There will be more and more models and application of models that will be developed over time. And so you just want to be aware of that and not get fixated on any particular model. Now, we'll finish up this introduction with looking at a tremendous quote we believe to wrap up your introduction to large language models. Chris, some of our community will not be familiar with Jack Shanahan, so just give a quick introduction of Jack, and then I'll talk about his quote and its relevance here.
He's fantastic. I met Jack when he was the director of the Joint AI Center. So if you look back, 10 or so years ago, DoD created the Algorithmic Warfare Task Force, which led in a pretty quick way to the formation of the Joint AI Center. And Jack was the first director of that for DoD. As an Air Force 3-star general, he took over the leadership of that early organization and has, all the scar tissues and all of the learning that comes with this exciting broad area around AI and AI development in DoD. But he's just he's a great leader, good mentor, and an active participant now in the follow-on to the National Security Commission on AI at a level. It's Eric Schmidt's initiative, referred to as the Special Competitive Studies Project, and Jack is very actively involved there.
Yeah, here's the best thing, Chris, I would say about Jack Shanahan. So he's a retired 3-star general. So we could say analytically he's in the 4th quartile of his life. And what does he do as soon as he retires? He goes to North Carolina State University, which has some of the most prominent data science programs in the country, and he gets a Master of Science in data science.
Love it.
That's one of the, just fantastic. But this quote here, we think, wraps up this introduction properly, because in the front end of it, as you have seen, Jack talks about the seemingly limitless opportunities that are being presented by the future that have humans and machines working together collaboratively and in teams. But he hits two very important things that we think you should have foremost in your mind as you become more literate and move toward fluency in this area. And the first is that any of these models, like any technical system, have capabilities, they have strengths, and they have limits. They have things you need to be cautious about.
Definitely.
Yeah. How many times have we heard now predictions on when we're going to have full self-driving autonomous cars? There have been a number of those predictions. It's almost like a cult now, and the end of the world is coming. They've been wrong multiple times. And I have one of the most advanced versions of that type of vehicle that you can buy. And I can assure you, it is not fully autonomous. I'm staying wide awake while I'm driving it, especially in certain edge case areas. And so Jack emphasizes something Chris and I have learned over the decades in working with technical systems to include advanced analytics and AI. Users, regardless of your role, need to be literate around the strengths and the limitations in order to intelligently participate in the dialogue and the decisions about where and how these things are going to be applied. And then secondly, and importantly, because AI does have transformational potential in the way we work and the way humans and machines collaborate, and even in the type of systems that we're developing, to include autonomous systems, we need to approach their application by rethinking roles and responsibilities, rethinking about how we're organized, about how our concepts of operation work, rethinking everything about the way we do business in the national security community by fully leveraging these machines. So we think Jack's quote here puts a really nice cap on this introduction to ChatGPT and large language models. When we come back, in the next segment, we're going to build on that foundation by walking you through the history of how these models have evolved and are continuing to evolve.
So, Frank, if we move this forward, and I think for everyone listening, it's important to get some headline elements around the history of this development. The broad area is natural language processing, and I've been involved with a range of teams over time where we are applying natural language processing tools. Natural language generation is a subset of that in what is represented in ChatGPT. But these four epochs are important. Now, start any historical discussion, potential for a urinary Olympic around why did you cut it off here or there. I wouldn't major in that, but these themes are important. So we have a research-dominated period from the 40s through the 80s. In 90 to 2000, you start to see some significant statistical methods emerge for NLP, natural language processing. 2000 to 2010, there's some substantial traction that begins to unfold in activities in this space, to include applied activities that are available in the consumer space and others. And then from 2010 on, what we're really living in and what you're experiencing now with the large language models is this deep learning era where it's risen into prominence. It wasn't that it was absent before, but it's really risen into prominence. And let's just take a look and put some of this into context. So from the 40s through the 80s, you could really think of NLP having a heavy emphasis on language translation. Russian was an early problem that got a lot of attention, but there were a couple of major limiting factors. One, a lot of the data was paper. So just staging what you needed to begin to train models was challenging, and data was a bottleneck in that. The work was done on mainframes, and there were some really innovative things that were done in the 60s and the 70s on mainframes from different manufacturers. But the focus was really developing rules for processing language. And some of this is important as we carry forward to today. Syntax and semantics are two of the core elements that people have grappled with over time, and they are dominant in ChatGPT. The difference here in this phase is that the rules were handcrafted. People were developing these rules. That's a distinction you want to carry forward into the future. Now, what happens? We kind of leave what some people call the AI winter. The 1980s were not necessarily auspicious when as it pertains to AI, and even the early part of the 90s in some areas. But for natural language processing, there were a combination of things that started to come together that began to open the door to change. You see a rise in the prevalence of digital data. With that rise comes the presence and the wider availability of higher performing workstations that can sit on the desktop. So Frank and I met in this era. I ran an analytics lab in an organization that he was a leader of. We had Sun Spark workstations, what you see in the background there on the right, the pizza box, fairly high performing workstation in its time, and you could perform a variety of tasks. And in that window, you begin to see the rise in some statistical methods applied to NLP for entity extraction, for entity recognition, for topic identification. Some of these are still used today. So I was running a team a couple of years ago, and we were applying support vector models in a particular context to extract items and to make judgments about topics. And the point here is these legacy models that emerged in this window still valuable today, used in a wide variety of contexts. But the 90s is a pivot point when you start to see the emergence of these new techniques in a digital data context that is emergent with new computers. Now, 2000 to 2010, really important sets of changes. One of those is in the right-hand side with regard to distributed compute. So if we take a workload, it's one thing for me to execute that workload on my laptop or my desktop. It's another thing altogether to be able to take a body of work and spread it over 20 or 100 computers and run it in parallel. This really starts to take off in this period, and Apache releases a suite of tools that become very important. Then Hadoop MR, MapReduce, is one of those. So I split the work, MapReduce, apportion it out to a variety of machines, and by using a common file system, the Hadoop file system, you're able to orchestrate the parallelization of that work. Really important. Now, secondly, in tools on the bottom there, you start to see the emergence of things that in open source, meaning they are developed and shared widely. They are not commercial off the shelf. They are open source tools like Python NLTK, Natural Language Toolkit. This is still used today. It's any data scientist anywhere that's working in Python on text is likely leveraging NLTK, and that emerged early in the 1990s. So you get a lot of traction here, but there are still significant compute constraints. That's one of the things that's really different as we move into this last phase, this 2010 to present where we're living right now. The focus is still on understanding and generating language. We want to understand it, natural language processing, but as a subset of that, generate text, as is happening with ChatGPT. One of the enormous steps forward is in the compute infrastructure. And if you look at those innovations, NVIDIA has just been a tenacious innovator in this space and around the graphical processing unit, or GPU, an extraordinarily high performance workstation and type that has opened a wide range of opportunities for tackling large volumes of work, parallelizing it so that we make it happen really fast. And we'll show you some speed applications on ChatGPT shortly. But you also see, and they're piggybacking on the continuing rise of social media, the prevalence of that data in the open, where it can be harvested and used to train natural language processing or generation models. And you see the rise of these new methods, and we're going to be focusing on one of them called a transformer. That's the era that we're in, where that has become predominant, supplanting what had been a really heavy emphasis on recurrent neural nets and convolutional neural nets, which, while very capable, had some significant limitations for where we are.
So Chris,
you
highlight something here that we would want leaders and just everybody in the enterprise to take away when they think about the AI solution stack for any problem. There is a lot of talk about data. Data is the new oil. Sometimes some of the shibboleths can cause me, frankly, to be a little nauseous. But yes, data is really important, and the proliferation of digital data of various types, image data, formatted text, unstructured text, et cetera, all very important. The foundational layer of the solution stack is computing. If you don't have computing that marries to the data and the problem, then you're Tango uniform. You have to have sufficient computing. And then you also highlight that, yes, I've got computing and data, but I have to have the right models trained, and then I have to integrate those models into software. And so leaders should take away from this, or everybody in the enterprise should take away from this. Yeah, data critically important. It is one component of a 4-part solution stack that you use in every AI solution.
Yeah, Frank, I'm glad you said that. And I think it's fair to say We've been through in these last couple of epochs periods where software gets a tremendous amount of attention, but the hardware layer is really important in this. And yeah, what's been accomplished, like with the Google tensor processing units, with NVIDIA and GPUs, now DPUs as well, very important. And it really sets up, I think, this next set of observations that we got as we iterated this material. You ought to walk people through this background.
So this is the deputy commandant that Chris alluded to in the intro, Lieutenant General Glavy. He is the deputy commandant for information. So think all of the Marine Corps' combat information as well as its enterprise information, and includes other things like cyber. And so he notes that Marines, and being a Marine no longer on active duty, this makes my chest swell up with language like this, that we take great pride in being able to adapt and innovate and overcome in any environment. By the way, there's a great movie line that he's drawing on there. But AI is no different. It is a means to an operational end. And so he notes that the Corps is committed to combat readiness. So he's keeping the focus on the mission problem, which is part of what Chris and I call our axiom zero.
Love that.
You have got to approach this with the clear definition of what problem we're trying to solve, what objective we're trying to achieve in the mission space. And so he notes that the Corps is experimenting with ChatGPT and large language models. It's doing it responsibly. And you would expect the Marine Corps and you would expect the rest of the national security enterprise as a taxpayer to do nothing different. So that emphasis on keeping the mission problem in the forefront and having the means conform to the end that you're trying to achieve, it cannot be overemphasized. And so we want to finish up this section by emphasizing this quote from General Glavy.
Yeah, by the way, Frank, and it to me, this sentence that General Glavy offered, we are experimenting with ChatGPT and LLMs responsibly. They're doing it, right? They're doing this now. That's not a casual sentence. They've had some war games where they have integrated this, working with partner companies like Scale AI, et cetera. They're doing it. And it's just impressive to me. I love the attitude, love the aggressive approach.
Yeah. So really good foundation, hopefully you have now, in an introduction and the history behind these models and how they're continuing to evolve. Now we're going to open up the hood and get underneath a bit, as we might say, and help you feel like you've got a bit of a hands-on perspective of how these models actually work.
So let's do it. Let's get under the hood and take a look at some of the features of GPT, Generative Pre-trained Transformer, GPT-3. So the evolution started in 2018, GPT-1. Successively, they have, this being OpenAI, introduced upgrades to it and new versions. We are currently on GPT-4. That has launched recently, but not all the features are in the open, and so we're using GPT-3 here to illustrate for you what it looks like a bit and some of the important facets. And want to keep this applied, so we will give you some handholds as we walk through this material to help you. The first thing I think that's important to emphasize is this machine, which has these four big features at the center here that we'll discuss, and then some adjacent elements. It is trained in an unsupervised way. So 1940 to 1980, handcrafted rules. People are sitting around handcrafting rules to language understanding and language processing. What is happening with this beast, it is ingesting enormous amounts of input, 1 trillion plus words for GPT-3. That OpenAI does not technically advertise the exact amount of input, but it's estimated in excess of 1 trillion words were ingested into the machine. Its deriving rules, semantic and syntax rules on its own.
Thus the term machine learning, Chris, correct? The machine
Yes.
is learning rather than being told what to do.
Yes, and it's an unsupervised form, meaning it's not being given examples of a particular thing. This is a dog. Learn how to identify a dog. It's just being given the input, and in an unsupervised way, it's establishing rich sets of relationships between words, patterns in the language, in sequencing and ordering, etc. Now, this capability has a vocabulary in the current instance of about 13 billion items. You might ask, how can it be so large when the English language, and you can start a fight, among linguists, how big is the lexicon for English? But think in common use, about 50,000 words.
It ain't 13 billion, I'll tell you that.
It ain't anywhere close to 13 billion. That would be a good technical characterization, Frank. Yeah, it's not anywhere close to that. And it's because this input is being what is referred to in NLP space tokenized. So think in Air Force terms, to stick with that analogy, a fighter. Well, a fighter would become a token, maybe truncated, maybe in its original form. A fighter aircraft might be a token. A fifth generation fighter aircraft might be a token. These combinations of things can become tokens, which constitute elements in the vocabulary for ChatGPT, and it's expansive. Now, on those tokens, there are then parameters attached. And the parameters tend to be, and we'll explain this in math space, vectors of features. And they're also in the model itself, 96 layers. These layers all are comprised of rich parameterized elements like attention heads and some other characteristics. But it's monstrous. That would be the thing to take away. Now, get this data point. I have a smartphone. Can I put this on my smartphone? I can run the app on my smartphone. I can run the app on my laptop. But to give you a comparative data point, if you put Microsoft Office on your laptop, that's about 6 gigabytes of data. This beast, GPT-3, estimated a little north of 700 gigabytes, not 6 gigabytes, Microsoft Office, 700 gigabytes to capture the richness of language, semantical issues, syntactical issues in the language, 700 gigabytes. Over 100 times, what would be present for you in putting Microsoft Office on your desk. That's just a vivid, specific point. It's running on GPUs predominantly, and it's expensive. It's a lot of compute power. So envision it that way. This is not a casual small thing. While we can run a neural net on a desktop machine or a laptop machine, this is an entirely different kettle of fish. Now, how does it work? Think about it as 4 major components in a transformer architecture. And on the left-hand side, I'll use the question and answer format, a user would submit a question to ChatGPT. The first thing it's hitting in the architecture is referred to as an input layer. And that input layer performs really basic natural language processing tasks. Some pre-processing, which can include stemming and stopping, depending on the tokenization and pre-processing approach. I eliminate articles as an example, a, the, and. You're tokenizing, so you're identifying specific elements that then flow to the embedding layer. And in the embedding layer, every token from the input stream, so using that earlier example, fighter, is assigned what's referred to as a high dimension vector, and we'll illustrate that in a moment. But we leave language and we go to math form of language, but we are leaving English as an example, and we are converting that into math and mathematical features. The output of the embedding layer flows into a transformer block. And we said earlier, there's 96 layers that comprise GPT-3. GPT-2 had 48 layers. GPT-1 had 12 layers. So we're getting more and more depth and breadth in this thing over time. But 93 of the layers constitute what is referred to as the transformer block. Each one is similar. We'll explain what those look like, but the purpose of it is to understand the input and then to generate and sequence an intermediate output. And then you hit the output layer itself, which is where what Frank described using that Air Force example. I'm taking the intermediate product that is generated in the transformer block against probability distributions, and depending on the task type, I'm flowing through to give an answer. And it's happening fast, like wicked fast, lightning fast, and we'll show you examples there. Now, the magic is making all of this math work. We'll explain an example there in a moment, but I first want to illustrate just vividly and specifically how this changes. So the Air Force was a prompt we illustrated earlier. That hits the input layer on the left-hand side. Every element in that sequence gets tokenized. And potentially you're creating combinations of token or combinations of elements into additional tokens. So the U.S. Air Force might become a token. Air Force might become a token in each individual one. Now that flows right in this graphic into the embedding layer. And in the embedding layer, every one of those tokens is uniquely assigned to what is referred to as a vector space. And that vector space is numeric. It is filled with features that describe what the machine has learned through its training about this particular word and its semantic context in language. Now, this is done in a language agnostic way because one of the functions of GPT can be to translate, but it's a rich set of mathematical features that describe the token. That then flows to the right into the transformer blocks, which has multiple layers, 93 layers. It stays vectorized. And in each one of those successive layers, you're refining the understanding and refining the output. Finally, we hit the output layer itself on the far right, and we get the kind of product that was illustrated in the graphic showed you earlier, and this would be an example. The U.S. Air Force is the largest and most technologically advanced Air Force in the world. That would be a sentence completion task and how it flows through the system quickly. Now, the magic here in this last decade, and there are limits on this, and we don't know how the limits are going to be broken through, and we'll illustrate that. But the magic here is really consequential. It's in the form of what are referred to as attention heads. So there are 93 layers in the transformer block. Every one of those layers has an identical core composition that's a part of the transformer architecture. There are up to 96, it's a configurable feature, 96 attention heads. Those process in parallel what is input. Once they have processed in parallel, that is passed to what is referred to as a feed-forward neural net, which creates a version of the intermediate product. Now, across all of this, and it's common in parallel computing, distributed computing, you've got to normalize inputs. It is not simple work that these people have figured out. And that would be the messages. This is very complex compute in making the deep learning system work. And not everything is on simply understanding the language. You've got to make the machine function effectively, and this normalization feature will do that. And then, unlike the predecessor capabilities, recurrent neural nets and convolutional neural nets, you've got to retain information in what would be referred to as long-term kind of memory. Now, for us, it's not long-term, but you're flowing this through layers 1 to 93. You're retaining critical elements of the information while you're improving your understanding, and you're working towards generating intermediate output. Now, get this. 96 attention heads. Not all of them are doing, well, they're not all doing the same thing. Some of them have a heavy weight on syntax. Some of them have a heavy weight on semantics. So as you're flowing the information through these attention heads, what they're doing is weighting or assigning a mathematical weights, importance to the input stream, which helps in the successive processing. What are we really dealing with here? What does this mean? Oh, given that context and the task, what does my response need to be? And you begin generating iteratively intermediate output. And as you move from left to right in this transformer block, you can think of it this way. If I'm in an athletic stance, I've got weight on both my left and my right foot, but it's not equal. And as you move right in the transformer block, you're shifting weight effectively. It's more on the intermediate product. And then ultimately, we are going to hit the output layer where, depending on the task type, is it completion, summarization, expansion, translation, answering, depending on the output type, we're going to kick out a product. And it's amazing to me what they have done with this. There are ways to influence its performance, but I think critical in it is just recognizing, in the midst of substantial compute innovation, not simply the cloud, but in hardware available on the cloud, like GPUs and tensor processing units. What a team at Google did was to mature some thinking that first emerged in 2014, but it's on this issue of attention and self-attention. And it really positioned the leap forward from recurrent neural nets and convolutional neural nets. And I think you can argue it is the thing that propelled this last 5-year journey. Now, interestingly, this was shared widely. Attention is all you need is a paper that you can pull down and read. And Google was a research house at a level they shared widely. They've shared open source software, etc. This recent frenetic blitz has caused some rethinking on that posture, and it mimics a point that Frank made earlier. Industry has to grapple with this too. You're going to have competition in this space, and the rules may not stay exactly the same. So we're watching carefully ourselves. Now, I think this closing thought, though, Frank, you and I were talking about this. Brett Vaughn is the chief AI officer of the United States Navy. I met Brett several years ago and was working with him around where AI opportunities are in the Navy and the direction that they are trying to move. And they have some pretty substantial efforts that are underway in the infrastructure via Project Overmatch, as well as discrete AI projects. But Frank, what was your reaction when you read just the top part of Brett's response?
I think what is key that he highlights, so before we said Glavy hit a foundational principle in keeping the mission on the forefront. The companion we think Brett Vaughn hits here, which is the Navy is leveraging the entire AI toolbox. Chris has referred a number of times to different types of neural nets. If you thought of the different mathematical or statistical techniques within AI as this spectrum, and we actually teach that in one of our courses and break out each part of the spectrum. These techniques we're talking about now in terms of their mathematical sophistication, as you just saw in this segment, are very complex. They're on the right-hand side of the spectrum. There are a wide variety of techniques, and the techniques need to get matched to the problem. What we can't do is what Chris and I have experienced very recently with a senior leader in a major national security element who came to an OEM provider and sat down and right out of the gate said, look, what I want to talk about is what you can do to help me bring ChatGPT into my enterprise. We understand it is exciting. There are department chiefs and there are political appointees, and everybody is frothy. And as we've just shown, we're excited about it too. We're users. It is helping us in our work, but it is a tool in the toolbox that is suited for certain types of problems and certain types of compute and data environments, as Chris has illustrated. So what Brett does as a service for you here is just point out that you need to be literate. Everyone needs to be literate in the national security enterprise on the full toolbox range and approach a discussion. You can think of it, we'll call it the Glavy principle, mission first, and the Vaughn principle. I'm going to marry the right tool to the mission problem that I'm trying to solve.
I think that's a great way to say that, Frank. And yeah, it really sets up where we ought to go next here on just strengths and cautions with this particular capability.
Now we're going to pivot to the discussion of strengths and cautions and certainties and uncertainties, having now set what we hope is a really strong foundation for you in literacy about ChatGPT and large language models. And we would say, starting in this section, you've seen and we've talked about tremendous strengths. We're going to show you another example, but there are also areas where you need to be cautious, and we'll show you some examples of that. So let's start with the strength. So here you have an article. This is an example of summation or summarizing. We took a New York Times article written by Jeffrey Hinton. He is an AI pioneer, was at Google for a number of years. And we took the article and we asked for a summary of the article. And you can see and read the summary here. It is a really good gisting or synopsis of the essence of the article that appeared recently in the New York Times that just talks about Hinton's concern with the evolution of these models and concerns about, the potential implications of and misuse of this technology and the risks that they could propose.
It's lightning fast.
Yeah, what you get here in terms of speed is you have a 1,300 word article with a really high quality summarization or synopsis that was done in 9 seconds. It's 86 words. It's about 7% of the original article. And again, you could read the 86 words and get the gist, the essence. And the models accomplish this in 9 seconds. If you think about kind of the average reading speed that you see there of 200 to 300 words per minute, or creative writing that is estimated creatively, if we were trying to do this, we would average about 5 to 10 words per minute. It's just massively impressive, the speed at which these models can work. Now, that's an example of a strength. Let's pivot to look at some areas where you need to be cautious. One of those would be in narrow topics. So we used a series of prompts here around an Air Force office known as Checkmate. It is a storied office that is existent within the headquarters Air Force staff, but is a hand-selected group of operators and other airmen and guardian that put together air and space campaign plans. You stop any Air Force officer and they would be very well aware of this Checkmate office. It's quite an honor to get selected.
Yeah, I mean, Frank, we've known a former director, known a number of people who've served in it. It's a really important office.
Yeah. So it has been around for decades. And so we give the prompt, how long has the U.S. Air Force Checkmate existed? And the answer we get back is it was announced in July 2021 by the Secretary. It's a patently wrong answer. So we give the model a second chance, in effect, by giving it another prompt in the same string. Was there an earlier checkmate? So it would be like if you and I were having a conversation and I gave you this answer and you said, was there an earlier version? And you'd be signaling to me. And so we're trying to signal to the model and give the model a second chance. And the model says, not to my knowledge. So when you get to narrow topics, you need to be cautious because, as you see in this example, there are opportunities for the models to just be patently wrong when it comes to narrowly focused questions. Now let's look at another area where these models can struggle, and that's in dealing with numeric values and numeric reasoning. So we put in this prompt. Do we understand correctly that glue is a fairly narrow set of natural language understanding tasks, but GPT-2 actually performs slightly better than GPT-3 in this narrow context? So glue is a benchmark, general language understanding evaluation. It is a benchmark set of tasks and data sets that have been created to have communities have a common place, a common frame of reference to test natural language models. And so we're basically asking it, using this benchmark, who performed better, 2 or 3? And you see the answer we get back. No, it's not correct that 2 outperformed 3. 3 actually outperformed 2 on the glue benchmark. In fact, 2 achieved a score of 89.8, while 3 achieved a score of 88.4.
You may have to just pause there for a minute and marinate in that answer.
Yeah. Well, you don't have to pause for too long. You don't need to be a statistician or a mathematician.
No, indeed.
To just realize that, again, where numeric values and reasoning are concerned, Chris ran another test where he asked the model, how many surface combatant warships are in the United States Navy? And the answer came back, and it was a very solid answer. Then a very similar question about another armed service in the United States. How many brigade combat teams are in the United States Army? And the answer came back that it was garbage. So wildly wrong. And so you just, when you're asking these models for numeric values and numeric reasoning, it's an area where you just need to be cautious. Now, in integrating these models, and as we've talked to you previously, you want to think about these models being integrated into a solution and into the solution stack. It is more than just giving someone access to a web service that exists now for ChatGPT. There are APIs that have been created to give programs, applications, interface to the model so that you can write unique applications to leverage one of these models. A good example, just yesterday, I was listening to Bloomberg, and there was one of the major travel web services that I suspect most of you have used. The CEO was on, and unprompted, as he was talking about what they're trying to do to serve their customers and differentiate in the market, as he said, within our app on the Apple iOS, if you have an Apple iPhone and you download their app, you get an API interface to ChatGPT, so that as you're planning your travel, you can ask ChatGPT questions using that API interface, and you can store the answers within their app, et cetera, et cetera. So leveraging the APIs is certainly one element, but we want you to think about integration in a fulsome way. So let's talk about a few others, one being prompt engineering. When we say prompt engineering, we don't mean timely engineering. We mean the engineering of these prompts, what is put into the model, the input, for a given use case, for a problem that you're trying to solve. Good example of this, Andrew Ning and Isa Fulford. Andrew Ning, one of the most renowned data scientists in the world, I would say, certainly within the U.S., And Isa Fulford is a technical staff developer at OpenAI. They've just put a free course out there. Several 100,000 people have signed up and taken it. I took it. It is a course to help developers with best practices for how to code prompts to best leverage the model for a given use case. So again, if you're a developer in that travel web service that we just talked about, how do I structure the prompts so that we're leveraging the model to get the best responses on travel related questions? And so there's a body of work that's going on around prompt engineering that is an important part of training. Similar to that or related to that, there is an iterative process in training these models where the models are tuned based on human feedback. And so it is another important part of integrating the model into a specific application for a specific use case.
Very different than how it's initially trained. Yeah, because you're now engaging humans to give some feedback on the quality of responses, but it's a type and it's a way that can improve performance.
Yeah. Then importantly, training, frankly, as we would say, this lesson being one example, training a very powerful way. We would encourage you to think about training as part of the overall integration effort. Training of developers, training of users on use cases, on strengths, on cautions, on limitations, on risk. We think training is a critically important part of the integration effort. And then, Chris, we've referred to it a number of times. Ultimately, a model, an AI model, whether it's a large language model or something else, it is generally getting integrated into an application for enterprise-wide implementation. You can have kind of discrete models for very selective tasks where the output literally is a table with a set of recommendations. But for enterprise scale implementations, generally you're integrating the model into software. And so part of your integration effort, very key, we talk about this in one of our courses, the best practices for integrating models into the software development process. So just think about integration in a fulsome way. These are 5 ways, but think about it as more than just giving people access to a model.
I think that is the message, man. It's don't just make it available and call it dusted and done. That's an unwise approach to how to integrate this capability into an operation.
Yeah. So, Chris, let's finish up this section on strengths and cautions with a statement by a senior state officer here. When you look at this statement by Garrett Bernstein at the Department of State, what stands out to you?
Well, a couple of things immediately, just putting him into context. Matthew Gravis is the Chief Data Officer of the U.S. Department of State. Garrett, the deputy there, and they have been intimately involved, actually, Garrett, with the Center for Analytics. So the enterprise-wide center that state created to address a range of challenges like this. And they've done some not inconsequential work in natural language processing. So when Garrett comes to this, it's from that perspective. And I've heard from he and others, they have done in the department some big webinars already that, 1,000+ people to come learn about ChatGPT at the high level. So contextually, that's immediately what I think about. I mean, how do you react to the bolded portion there in his comment?
Yeah, I think he's doubling down on what I called earlier kind of the Glavy and the Vaughn bride and groom principles of mission focus and suiting the right approach to the mission problem that we're trying to solve. He says we're early in the journey, and it's something we're going to finish up with in just a moment. Chris has alluded to it. There is a lot we don't know right now. So I think it's very encouraging to hear this kind of wisdom from a senior state officer in the AI department early in the journey. And so focusing on user-centric pilots, it'd be another way of saying focusing on mission problem pilots, where you can test and prove, test and learn before you go to enterprise scaling. It's foundational. But again, it's in that balance that we talked about in the beginning between hand wringing and hype. So just great deal of wisdom from Garrett here in this quote, we believe.
So we'll close this out now with focusing on some areas that are certain, effectively with respect to GPT and the large language model family, as well as some uncertainties. And you should be clear on both. It's important on both. With regard to certainties, we are really comfortable saying that if you will think of integration broadly, as Frank just touched on, the 5 elements, inclusive of training, inclusive of some software development and process redesign, to get at what Jack Shanahan said, rethink the roles and responsibilities between machines and humans and make sure we adjust fully for that. If you do that, these 3 areas seem really highly likely to pay off. Question answering, we've had chatbots for a long time. This is an improved ability to address that problem. Summarization, we've shown you it's blazingly fast, and there are a lot of things in the national security enterprise. We produce prodigious amounts of text.
Yeah, Chris, forgive me. Everybody, and I can think now of multiple former clients, everybody who has suffered through the sad little land of knowledge management should be really excited about how to potentially take this technology and actually do something to manage their knowledge.
Yes, and this pathway to quickly get to summaries so that you can discover the things that really matter are there. And in translation, the performance is high, whether language translation, linguistics, or software. There are a lot of high quality pointers to promising futures. Now, that being said, definitely some items that we need to be conscious of. This Geoffrey Hinton, who we mentioned earlier, was really instrumental in aspects of the development of these capabilities that underpin the Google models like BERT, etc., as well as effectively by transfer what OpenAI is doing. And one of the concerns that Hinton has highlighted is that as this text becomes more and more realistic, more and more human, it's going to make it hard to discriminate misinformation, and it's going to become so much faster. Think about that. We can generate content in a 60th the amount of time in general summarization terms. So how will that get navigated? That the certainty is bad actors are going to use this. Bet your net worth they're going to use it. The uncertainty is how we can mitigate and prepare, but we should be conscious of this area, mindful of it. Now, here's another one, and this is really important. Like, put down everything else and concentrate for a moment on this. Hallucinations. They have been present in every iteration of GPT. They do not go away with GPT-4. I want to illustrate what is going on. I'll give you briefly the background here. So I was doing testing on this and taking a family of questions, having GPT or ChatGPT identify articles. I was interested in prominent articles, popular articles, articles that might be suitable for a certain kind of audience, all around Army-related issues. It would generate responses, and I tended to do it in triples. I asked for 3 articles on this, 3 articles on that. Uniformly poor performance. So if you look at this response, this is the verbatim response from GPT. It was the first in the batting order on several for a particular prompt. And it was point to me 3 articles that address the Army force redesign in the early 2000s, shifting emphasis from the division structure to the new brigade combat teams. This was the first item.
So, Chris, for non-Army members of our community, very important to foot stomp here. This was a massive transformation in the United States Army. There was a lot, read tons of articles in a wide variety of journals written about this topic.
Yes, that would be a good characterization. And you see the title here, The Evolution of the Brigade Combat Team in the U.S. Army, Implications for Combined Arms Maneuver and Expeditionary Warfare. Looks good. Jonathan D. Moyer in the Military Review in 2012. And it says this provides an overview of the evolution of the BCT concept and its impact on Army force design. Now, every element in that description is fabricated garbage. Every element in this description is untrue. Every single element. The title does not exist. The author exists, but he doesn't write on these topics. Jonathan Moyer, as an example, is a professor at Denver University. He's written quite a lot, even in the foreign affairs area. He has an article that was written in War on the Rocks for those that are in the national security environment. But he has not written this. Have checked his publications list, have checked Military Review and the publications for that year and years around it, have searched generally for this topic. It doesn't exist. It's a fabrication. This is a hallucination. The machine is taking my input, and through that exquisite processing to understand what I was after, etc., it is writing for me something that is semantically accurate, semantically well-crafted, and syntactically good, but utterly rubbish with regard to fact. And that's a challenge that it's not clear how it gets addressed. So earlier, if you think of the historical evolution that we walked through, there were data problems, and we just couldn't get the data into machines. Then there were compute problems, and those started to open up, and we had families of software that enabled highly distributed parallelized compute, new families of models. It's uncertain to us how this gets solved. It's probably not a compute issue, although compute will be implicated. It's probably some kind of modeling and technique issue. But right now it's not clear. What is clear is it's not solved in GPT-4. And when you look at where we're going, let me contrast what's happening. These are benchmark performance elements of GPT-1, the first evolution, 2018. And then in the bottom, characteristics of GPT-1. So you'll notice, as an example, in the bottom, there were 12 layers. And you remember what we walked through in the depth, the layers of the model. Well, in GPT-2, we went to 48 layers and 1.5 billion parameters. GPT-3, we went to 175 billion parameters, 96 layers. And look at how performance changed. So let me draw your attention to Lambda as an example, which is a particular benchmark around language. From GPT-1 to 2, we almost doubled in performance. From GPT-2 to 3, that performance starts to flatten out, right? GPT-4, all the facts are not out yet. They've been a little bit discrete about what they share about the model, so the characteristics in the bottom portion of this, and then the performance is not fully uncloaked, and we haven't done that here. But what is, I think, plain, and our research iterations would illustrate this, GPT-4 does not solve this problem. ChatGPT Plus, which is what links to GPT-4, manifests the same behaviors that we were seeing with GPT-3. So in that context, I think this next thing is helpful. Frank, you ought to introduce Chris Grubb just to
Hey, Chris, if you would just for a second go back to that previous page, let's just make a generalized point that people should have in their AI literacy. And we'll make an analogy to something that most people understand their day to day lives. As you move up the complexity level in any given model, or you increase the compute or increase the data, it does not necessarily mean you're going to get linear increases in performance. And Chris and I have seen this on teams in just, more use cases than we can count. But there sometimes can be the implicit assumption to include among data scientists, especially young data scientists who are really excited about more advanced versions of models, just a natural excitement and a good thing. Just be wary as a generalized principle, and this gives you an illustration of it, where driving increased complexity in the compute and the modeling, et cetera, is not necessarily going to get you linear gains. More calories ingested in a given day is not going to necessarily translate to better human performance in your life in a given day. There's a point at which there's a diminishing returns. So, Chris.
Yeah, Frank, I'm glad. Yeah, glad you went back to that. But if you look at this chart, just on the bottom of the benchmarks, language inference, as an example, and you look at GPT 2 to 3, right? We moved about 2 points in performance on the language inference benchmark. And look at the magnitude of the change. It doubled the layers, right? Doubled the layers.
Yeah.
Look at the increase in the number of parameters. And parameters are the heart of language understanding and generating the intermediate product. They hardly moved. Yeah. Right. So the model is becoming bigger and bigger. And with transformers, that's what has to happen. Generally, people would say this kind of model, the bigger and more complex and sophisticated it gets, the better the performance. But I think what you're highlighting is key. There is some point at which the utility curve turns here, and that's an uncertainty in where we're headed. And it's uncertain how you solve the problem of hallucinations. That's not fully clear at this point. Yeah. So with that, Frank, why don't you introduce Chris?
Yeah, Chris Grubb is a master data scientist that we have worked with for a number of years in different capacities on teams on really complex problems. And Chris is really unique in that spectrum of techniques that we talked about that range from descriptive statistics to inferential to optimization to simulation to the type of deep learning techniques that we've been talking about here with neural networks and large language models. He just has very competent experience across that full range. And he is very mission and problem focused. And so in kind of tactical, strategic terms, he's a brilliant and just a bone-crushingly strong tactician in this space.
He really is.
But he is also a strategic thinker. And Chris, I think, you can draw that strategic thinking out with this quote that he has.
Yeah, I think that there were several things as we iterated with Chris, as with the others, that jumped out. But this in the upper, the first one that is highlighted there, these capabilities will generate, it's what they're designed to do, plausible sequences of text. And that's what's at play with hallucinations, right? It's entirely plausible, right? That answer was entirely plausible. But what his second point is there, that second element that is highlighted, this is not reasoning. It's not reasoning based on facts, concepts, or truth. It is a probabilistic model that understands relationships between words in sequence, parts of speech in sequence, and semantic meanings of words, and it then probabilistically kicks out an output. It's not unimportant, but we should not mistake the need, the criticality of having humans involved to take this and run it through. And that's really Chris's final point, is you've got to have that. You've got to have humans stay in the loop on this and verifying the truth and even owning the final result.
Yeah, learning and thinking, two sort of foundational activities for an artilleryman, a logistics staff officer, for an intelligence analyst. I pick all of the, specialty codes, occupations in the national security enterprise. Learning and thinking are two critical skills that humans are going to have to continue to perform. In fact, Chris, I would say this to our community: these models, which are tremendous aids, to include tremendous aids to our learning, or they can be, they actually put greater emphasis on our learning and our thinking skills because of our ability to be susceptible to misinformation, disinformation, hallucination, et cetera. So.
It's a good area for people to fight about as we go forward, because it illustrates Jack Shanahan's point. We've got to think fundamentally about roles and relationships between humans and machines as we go forward.
So we'd kind of bring this to an end with highlighting three broad principles. I think we have illustrated the first here in talking about uncertainties. We don't know where this is going, and there are some real limitations and some real concerns that, as Chris showed in those technical parameters, it's not clear on the surface that there are easy solutions to some of these problems. Now, the people that are working this, as demonstrated by the success thus far, they are tremendous. They are gifted. And so the sort of raw technical performance could continue to advance forward. Certainly the integration that we've talked about and applying these to specific use cases, that is going to rapidly advance. But in terms of where all of this is going, there's still a great deal of uncertainty, and thus, again, the importance for leaders to be on the balls of the feet, be learning, be thinking, be paying attention, and being engaged in the decision making. We would say, secondly, as we've just alluded to, you have to remain an expert in your domain. Maybe even more important than ever. Maybe it's somewhat paradoxical, but as these machines become more and more capable, it is more and more incumbent upon us as humans to be experts in our domain so that we can evaluate the value, the fidelity, the veracity of the output that we're getting from these machines. And so lastly and importantly, the use of these models involves integration into a solution stack, into a workflow for a given mission problem, mission task. And we would just encourage you, think about integration broadly. Don't think about it as just giving somebody access to the model. Take those 5 areas that we talked about. We think those are helpful in you thinking about integration in a fulsome way.
100%.
So, Chris, last quote that we'll wrap this up with, and appropriately so, from another one of our just master data scientist colleagues, Mike Green. If you'd introduce Mike to our community.
I have worked closely with Mike now for about 6 or 7 years. Mike was classically trained in math at University of Chicago, subsequently did the applied stats program at Harvard, but most importantly, he's performed and led a lot of advanced work in machine learning and around AI, also just a range of advanced analytic tasks. He's one of the sharper people that I have worked with over time, just very gifted in taking apart mission problems and then looking at ways to solve them. What I really appreciate about him as well is he keeps up with the academic research. Mike is just one of those guys who not only is doing the work, but he keeps up with what's happening in the field really well. How did this bolded portion strike you, Frank?
So what Mike highlights here, I think, is we have shown some concerns, some cautions some uncertainties, hallucination, narrow problem sets or narrow tasks, numeric reasoning, etc. But back to balance, there's tremendous hope for these capabilities, reducing toil of workload on human beings, advancing the performance of humans and machines collaborating, new types of capabilities that Jack Shanahan alluded to. And what Mike basically points us to is there is tremendous potential here, but there's also hard work that we need to do in training models, in being able to explain them to users, in safety testing, in kind of verifying output, and then, as we've alluded to, in integrating them successfully. But if we focus on the hard work and we don't kind of get all conceptually wrapped up in the happy land of hype, but if we put our head down, roll our sleeves up, do the hard work, there's tremendous potential here.
Love that. Love that.
So Chris and I appreciate your attention to this lesson. We would invite your attention to two things as we wrap up here. First of all, if this lesson, most importantly, has been useful to you, then share it with others in your network. And there's a very simple way to share it. You can just point them to AIleaders.com. It'll be prominently featured at the top of our webpage, and they can get access to this lesson free of charge. And so we would ask you, if you found it of value, to share it within your network, because, again, we want to create AI literacy across everyone, literally everyone in the national security enterprise. And then in terms of AI literacy and fluency and going beyond this lesson, Chris and I started by disciplining our experience to a book that you see here, where we captured axioms and leader practices for the leadership of AI. We saw a gap there in the written works, in books and articles and in courses. And then there are 4 courses. The AI for Everyone, as the name implies, is there to help with literacy across the entire enterprise. And then there are 3 courses that are focused on fluency in AI leadership, depending on leader role. Again, you can go to the site if you're interested in more information on these courses, AIleaders.com. But we thank you for your attention. Our desire is to help leaders in the national security enterprise so that America and her allies win this global technical competition that is going on in this century by leveraging AI. So thank you very much.
Indeed. Indeed.